enough, no? So what I do is I'll adjust VC say for 5 volt. Means I'll vary the VCC in such a way that I'll vary this voltage so that the drop across collector emitter will become 5 volt. I'll keep this 5 volt, then I'll vary this VBE. By varying this EMF of this cell, I'll make it VB 0.1, then next 0.2. Then I'll note down the current here. How much of current in this microammeter. Fine. So this, by varying this, even this voltage will change. So how it is possible? Come for this. If you vary this VBB, this VB also will change. This IB will change. Both IB and VB will change. So therefore here, for VC 5 volt, I'll vary this VBB. Then I'll note down this VB and IB. The curve, what I get is then I'll increase VC. Five volt. This is for 10 volt. For when we see 5 volt, I'll get a curve like this. When we see 10 volt, I'll get a curve like this. Now we have to justify reason why it will shift towards right. Any reason anybody wants to think? Any reason can you say? Or maybe this is 10 volt, this is 5 volt. Why for different voltages the curve will be different here? Why the curve should be? I'll do one thing. I'll draw a horizontal line. I'll put one horizontal line. I'll put an horizontal line. What do you mean VB? Forward bias, no? It's a forward bias. So as I increase VC, for the same current to flow open, I should increase this forward bias. Able to get this? You look at further. Look at this. No. If you see this, as you increase, so what happened, like as you increase VC, the curve will shift here. Suppose we are at this particular point where VC 5 volt, we are here. If you increase VC, so to have the same current, you should increase forward bias. Any reason why do it will happen? So you should go back to the circuit here, no? Let's go back to this one here. No, as I will increase collector base junction, O is lightly doped, the base is lightly doped, no? I'll take help of this particular thing. I'm asking you to, this way collector base junction is reverse bias. So when you increase VC, what happened to width of depletion layer will penetrate more into the base than collector. Any reason? Because base is lightly doped. So I think we gave some colors, no? I don't remember. Oh, yellow and green. You look at the width of depletion there. I'll show it more into the base than collector. Any reason? Because base is lightly doped than collector. So if I increase the VC, nothing but shall I say I'm increasing reverse bias, then the depletion width of depletion will increase since base is lightly doped than collector. So what happened to penetration of the depletion will be more into the base than collector. Got the idea? Because what is this prime reason? Prime reason is what? Lightly doped. I know this is moderately doped. Compared to base, shall I say collector is heavily doped. So if we increase reverse bias, depletion level penetrate more into the base than collector. Will penetrate more into than collector. Then what happens? The effective length of the base will decrease. If the effective length of the base decreases, the electrons which are flowing here, you see this one, so let's say some 100 electrons, the electrons which are coming here, these electrons, what happen? Either forward bias, they'll enter. Then here what happen when they're moving like this, when they're moving like this here, when they're moving like this, they'll encounter less base length, no, less recombination because the effective length of base decrease, less recombination. If less recombination, less will be the base current. Because what is the base current? This base current is due to recombination. So I think I'll start like this. These are 100 electrons. They come like this. Forward bias, they'll enter here. Here this 100, here 100, here they become 95. And the remaining will come here. So from where open here, the another 95 should come from here. Another 95 should come from here. So here what will happen to all together? The recombination here, the amount of recombination decreases, no? Because if the effective length of base decreases, where the recombination can occur here only, cannot occur here. Am I right? So here, as you increase the reverse bias, the depletion will penetrate more into the base. So then the effective length of the base decreases, the recombination decreases. If recombination decreases, the base current decreases. Now to have the more base current, I should increase the forward bias. That's the reason. Got the idea, no? So as you increase the VC, the reverse bias across collector base junction increases. Then the depletion will penetrate more into the base. Then effective length of the base decreases, recombination decreases, base current decreases. To increase base current, what shall I do? I should apply more forward voltage, forward bias voltage. So therefore the curve speaks like this here. There's a reason why the curve will shift here. Now here if I plot the, I'll take it out this because it's of no use. This one just to make you understand I brought it. Like this you have to put it. So now what happened here, we'll take a slope. You can calculate for any curve. So you calculate the slope. So this will be delta IB. We'll get input resistance. So what is the slope is equal to delta IB by delta VB. So at VC certain voltage, at VC. Now delta IB by delta VB will become reciprocal of slope will be the forward resistance or input resistance will call. RI or RF. This should be equal to how much? Delta VBE by delta IB at certain value of VC at 5 volt, 10 volt. If you calculate at VC 5 volt, 10 volt, it will just vary by few ohms. Like here if it is 10 ohm, slightly to be different. So at what voltage you're calculating that you put. I'll take just average of that. So it's going to offer that average input resistance. Like this, I'm able to calculate now what is the input resistance offered by this transistor to the signal. And there is nothing but forward resistance, what you can call it. So I'll take it out this. Again, some of you are getting confusion. Let it be just total, there's the input resistance of the C configuration. Because we'll follow the symbols which are there in the book. Now, similarly, let's come for output characteristics. Okay, this I think, can you remember this? Later on, I'll write down the reason. Now, time is not there. Let me finish off output characteristics. Now, I'm going to keep IB constant. I'll vary VC, then I'll note down the IC. How do they vary? Let's check it here now. So, what is the output characteristics? It will be this will be ICE. This will be in milliampere. VC, this will be in volts, 1, 2, 3, 4, like this we can. And this is different values of IB, 5 microampere, or say let's start with 10 microampere. 50 microampere. There are regions are there. I'll mark the regions. So this is called as cutoff region. This region will become active region, and the remaining, this will call this as active region. Not exact boundary, so some, I'll put like this. Two regions are there. So the green color is what? Saturation region, and this is called as cutoff region. And this shaded one, this is called as active region. If you want to use as an amplifier, your transistor should be in this region. If you want to use as an on-off switch, it should be here. So what do you mean by on-off switch? If a current flows, so if the output voltage, in terms of output voltage, like here, if transistor is here, no current, then you can say off. If current is flowing, then it's on. Like this, if you operate between saturation cutoff, it will become on-off switch. If you want to use amplifier, you should bring like this. So on off switch, what I should do, I should just look at the collector current. If collector current is almost very small, you can see, but voltage is high, output voltage is high, output current is low, it will become off switch. Then if current is more, then it will become a on switch. Like that, based on current, we are saying that one. So if you operate in this saturation and cutoff region, not only saturation, it cannot be that one. On off. So you should operate in this one. If you want to make it on off, you should make it to fluctuate here. If you want to use amplifier, you should bring it here. So to that purpose, what happens, you should adjust the value of RB, VBB, VCC. It all depends upon this one. How you adjust these values, what happens, that will, in that region, the transistor will operate. So how to make the transistor operate in different region? Because I gave boundary, 3 regions I marked it, no? So how to make it, just depends on these values. What values you pick up this, in that the transistor will get operated. Transistor will not say that, okay, now today October to Gandhi Jayanti I'll operate in active region. No, nothing to do that one. Transistor will not decide. We are going to make transistor to operate in various regions. Who will decide in which region it will get operated? These values. So therefore, these are called as the biasing networks. What they do, they will bias transistor. They will make it to operate in different regions by choosing different values of RC, VCC, VBB, RB. Got the idea, no? This is, so now if you want to use amplifier, keep adjust the transistor's values in such a way that it should come here. If you want to use as an on off switch, you should operate in these 2 regions. No. So what is the use of this one? Means how do this expansion of graph your IIT professors or NIT professors or the engineering professors are going to explain. I need exactly some around 15 hours to explain this graph. Not possible. So I'm just going to leave it out. If you give time, I'll explain. 15 hours I need, not one to. Almost we should go to learn everything transistor. That's why in the books also they just skip it. 15 hours, not 1 to 5 hours. You need, because you have so many things almost around some. I'm showing only 3 currents. Altogether around some 22 currents will be available here. Minority carrier current, all so many things will come. We are not going to this one. If you just go to the digital library, type it note transistor, you'll get almost around 4,000 books on this. What are the 4,000 books? All 4,000 books based on how to use transistor, various applications. You take any electrical electronic circuit, there's a basic element. This is a basic element. It's a very versatile device. How you are going to use, in that way it's going to come its application. So I'm skipping part. Why only curve like this? Just like a information you are going to gather. What all you can find out from the curve, let's find out here. So let me calculate the slope. So if you calculate slope, what we get? So they're not a straight line. So we have a slope here. So if I'll magnify the diagram. Yeah. So are you looking at the some slope? So we have some slope here. This will become delta IC, delta VC. So what is the slope is equal to? Now, this is for output characteristics. So what is the slope is equal to delta IC by delta VC at certain value of VB, at value of IB. Reciprocal of this one will give output resistance. In the books what pen they have given certain like this, not divided it is, or you write at IB, at certain value of IB. So what is voltage by current? They'll become output resistance. So therefore we'll call this as RO. The symbol is output resistance here. What is resistance offered by collector emitter terminals? The resistance offered by these two terminals. Usually what is delta IC? Milliampere. Delta VC. So if you go and check it, no, this one, this will be of order, it will come of order kilo ohm, 10,000, 20,000 kilo ohm. It will be very high. This is output tension. Okay, next again, I'll let me take in another graph. And the same active region. See, I'm not giving some demarcation exactly, just rough range. So what is the best thing is like, how to calculate sir active region? What is the best active region? Means like a given some boundary not very specific. For a given transistor, there will be maximum possible current it can withstand. If any current more than that, it will burn out. And for any given, like a transistor, oh, the curve is not there here. For any given transistor, there's a maximum voltage VC, reverse bias. If you apply more than that, the collector base junction will burn out. You come for this. As I keep on increase collector emitter voltage, the reverse bias will increase. No, is there any upper limit? It's not a Zener diode. Is there any upper limit? S breakdown voltage. So therefore, for any transistor, so what happen? We have this upper limit. So what I do is like exactly I'll go for half of it. So what is IC saturation? Suppose at 10 milliampere. I'll operate in 5 milliampere. There's the best region where I can use it as amplifier. How to identify active region? Somewhere nearby half of IC saturation, half of VC cutoff, maximum cutoff. Means breakdown. Suppose say 20 volt is there. So you keep operate transistor somewhere in this region, 10 volt VC. Maximum collector current 10 milliampere. So choose collector current 5 milliampere, and this is say 10 volt. That will be the active region. Even this is also active region. The best thing is go for half of the IC saturation and half of the breakdown voltage, VC value. Now, what are other things? So you just extend these lines. I'll bring some other color. No. So this will be, I think color, you are able to differentiate. You just plot like this. Take some these things. Then, so you calculate this delta IC. And this will be delta IB. I'll take the ratio of this. This called like a current gain in CE configuration. And this symbol is what I'll call beta. This is given by delta IC by delta IB. This is something very important. And usually what is IB? Microampere. This is milliampere. So what is the value of beta? Will be very large. it will start from some, usually if the transistors, no, it will be some from 32, it will go up to even 500 practically. So it can take values of this particular thing. The higher the beta value, the better the transistor. So when you go and purchase the transistors, no, so what they ask you, they'll ask you what should be IC saturation, what should be the beta. Means now this beta is a given fixed value. The transistor will be so designed. Don't think that by varying this you'll get it. So this alpha beta are fixed quantities for a transistor. So what is alpha? Alpha was IC by IE, no? So this is called like a current gain in C configuration. This is called like a beta. So greater the value of beta, the better will be the transistor. I can use it very for applications. Now let's come for some relationship. IC equal to V, no? IB plus IE, no? So let me divide this by IC, this equation. So what is IC by IC? This will be 1. High B by IC will become 1 by beta. High E by IC. Okay, thank you. Yeah. What is the, can you go for alpha? Alpha definition is what? I think somewhere I brought it here. Yeah. High C by IE is what alpha, no? High C by IE is alpha. So then similarly now, so IC by IE is alpha. What is IC by IB is a beta. So the relation between alpha and beta. So if you want to get the relationship, no, so this will be 1 minus. So what is beta is equal to alpha minus beta is equal to, it will be alpha by alpha minus 1. Oh, some. I'll rewrite in another form. This will be 1 minus 1 by beta, 1 by alpha. So alpha equal to beta minus 1 by beta. You can bring it any form. So like this, the relation between alpha and beta are there, that one. So what are alpha, beta? They are the parameters of a transistor. When I'm designing a transistor, I should see that dependent. So depending on the value of beta, the cost of transistor will be different here. For different values of beta, the cost of transistor will be different. Oh. Okay, that's one. I think somewhere I messed it up here. Huh? Symbols. Okay, I got it. IE is equal to IB plus IC. So let me divide. So IC by IE, 1 by alpha, 1 by beta plus 1. So what is alpha is equal to beta by 1 plus beta. Or you can simplify for alpha. Okay, the relation between alpha and beta, that's the equation you remember. So if you know alpha, you can bring the beta. If you know beta, you can bring alpha. I change it, IE equal to IB plus IC. Okay, this is about the output characteristics. So what all output characteristics, output resistance and beta of a transistor you can calculate. And similarly, input resistance, input characteristics, it will be input resistance, what you can calculate here. So this is about the only the transistor. Just now what happened, what we learned, the transistor here. Means now like I want to use that as a switch. So what happens, you should adjust the values in such a way here. You can bring that in the either saturation or cutoff. Then become on off switch. If you want to use amplifier, operate in this region. Got this? So there's a thing. So one more, let me introduce. So as we have this equation, no? VCE. So let me plot VC versus IC graph. So this is VCE, this in volt, milliampere. How the graph will be? The graph which I am going to get will be of straight line, and there should be the VCC. Put IC 0, and there's one maximum possible value where VC will become 0, no? And that is what the IC max or IC saturation will call it. No, sir, what is operating? What is that active region? The active region, half of VCC and half of the maximum current what it permits. This is called like a operating region or active region. So active region means not only this, called like a Q point, operating point we'll call it. Anything anywhere nearby it, this will become active region. What about this? This will become the cutoff. This region will become cutoff, and this will become saturation. So we don't have active region one point anywhere nearby it. Suppose say this is 10 volt. Okay, anything this 5 volt is what preferred. Even if it is 7 volt, 7 to 3 will become active region. So this everything will become active region. So like this is what you can put it here. This region will become active region. This is cutoff. This will be saturation. So what is a cutoff? You can see no current. What do you mean saturation? Maximum current through the collector. This is called like a DC analysis here. So in books, I think if you see the integrated book, they have discussed this one. It's really a little bit very useful for you when you plot the VCC versus graph. No, so what about the active region? This is like this active region. This graph are a little bit different. This is IC versus VC for different values of IB. This is just to calculate. Why do we use this graph? To calculate the beta of a transistor to get the output resistance. For that purpose, when we are using transistor, I'll prefer this one. So if the transistor is such a way, that means like, sir, like a VCC, okay, 10 volt you pick up. How to pick up operating point means the VC should be adjusted in such a way that it should be off of VCC. So VCC 10 volt I pick up. Then who will decide VC 5 volt off of this one, the value of RC, no? So therefore now what becomes very important? These resistors. This will determine where, in which region the transistor is, in which region it is lying. Whatever values you cannot combine, connect here. You have to choose the values such a way that the transistor, if you want to use as an amplifier, you have to pick up these values in such a way that it should be first in active region. Then you give AC signal, it will amplify it. If it is in saturation cutoff, it will not amplify. If it is in active region, it will amplify. Okay, got this now? So any values of RC you cannot pick up. You have to choose the suitable value. There's overall the theoretical background. Okay, evening 1 hour I'll take class. We'll finish off this amplifier. Evening I'll intimate the time. Okay, thank you all of you.